I would imagine that the most likely thing you might say off the top of your head is, well, I would count them, right? Which seems reasonable, right? Because if you're going to estimate a number of something, counting them is often the way to go. Because I was going to say, what's the number of letters on the screen right now? Well, I might say, well, we've got T, H, I, N, K, so that's 5, and then we go from there and we start adding them up. But of course, what's the problem with that when estimating the size of a population of organisms? Well, you might immediately think of a couple of problems. One, whales live in the water. It's difficult to see them all, right? They're not even all necessarily surfacing or even in the same immediate place in the water at one time. And so how are you going to count them? And if you count one that comes up above the water and go, there's one, when it goes down again and another one comes up, is it the same whale or is it a different whale? How can you be sure? So it seems like a very sketchy way to just say, I'm going to count the number of whales. I'm not sure I would have much confidence in the count that you come up with. I'd probably be prone to think it was an underestimate, if anything, because the odds that you would see every single whale in a short period of time in some meaningful area is probably going to be pretty slim. Now, if you were asking about a population of daisies in a field, then it might be a heck of a lot easier to just go out and count them. But of course, there might even be better ways of doing that as well, because even though those daisies don't get up and move, it may be a daunting task to count every single one in a field, and you may be able to better estimate the population size without counting every single individual. So let's actually think about two more sophisticated ways that biologists use to estimate the size of a population. The first way is sampling quadrats. Now, what is a quadrat? Sampling, obviously, is just taking a sample of something, not the whole, but just a part of it. But what are we sampling if we're sampling quadrats? Well, quadrat is just a fancy word for a square area. And so what we might say is, let's say we wanted to sample the number of individuals in a place. Let's say daisies in a field. Go back to that example I just gave you. And I said, boy, you could count them, but that's a lot of work. Like, why would you want to sit there and count 1,000,000 daisies? Let's say there are 1,000,000 daisies in this massive field. That seems like a totally unnecessary level of counting, when you could arguably get close to the number of 1,000,000 in a different way. And that is that you would put out these small squares called quadrats. It might be like 1 meter by 1 meter square, so a meter squared. And you could do this by making like a plastic frame, and you could put it down in a place and count all the daisies that are in that square. Now, that's obviously going to be far fewer than 1,000,000 and a lot easier than counting that whole field. Now, the simplest thing to do after that is to say, look, if this field is 100 square meters and I counted 30 daisies in 1 square meter, how do I scale that 1 square meter up to the 100 square meters? Well, you probably thought of it. You multiply up. So you would take the 30 daisies in 1 square meter and say I have 100 of those. So I might have 30 times 100 or 3,000 daisies, right? Now, of course, the bigger and bigger and bigger the field is, the more your extrapolation leads to a larger population size. So we might get back up to that ultimately with a big enough field, the 1,000,000 that I referred to earlier, without having to even count those. All right, so we think about this, and let's scratch our head a minute and say, wait a minute now. Doesn't this assume something? Doesn't this assume that what I learn about this 1 square meter somehow tells me everything I need to know about the rest of that field? Well, of course it does. And that's why what oftentimes biologists will do, or most of the time biologists will do, if they're doing this right, is to count many quadrats. And so they might count 100 quadrats in this huge field, and they would put one down in a random place. And then after they count the daisies, put another one down in a random place. And so you might be able to count 1,000 square meters by using 100 quadrats. And what you're doing is sampling 10% of that total area, which is 10% of the work when it comes to counting. And the idea is by replicating those quadrats, by having numerous ones put in random places, you're getting some idea of the population size, even if what happens in this place isn't representative of what's going on in all of the places throughout that area. And so the more you sample, the more quadrats in random places, the more representative your samples are going to be. And so that when you take the average number for a quadrat across all of those samples, and then you multiply that up to the full scale, that average number better reflects what's going on over this whole area than a single quadrat number does. And so that's the idea here, is that you have to add in those elements of good design, randomization, and replication, to help you get more information about what's going on in this whole giant area. You wouldn't just put one single quadrat down. All right, so that's one method, and it would work well for daisies. Now let's consider another method that biologists use, and that's mark and recapture. So mark and recapture, the name simply states what it is. You would take an animal, you obviously have to capture it first, and then you would put some identifying mark on it. It could be something that you draw on it that's visible. It could be you might clip feathers, or you might clip scales if it has those. You might shave a bit of fur and put a little dye on the skin. Whatever you have to do so that the animal is going to be recognizable at some time in the future. You want to mark it in a way that's semi-permanent. You know, it lasts long enough that when you come back a second time, you'll be able to see the animals that you've marked if you catch them again. And that's then what you do. You go away and you come back a second time. And at the second time, what you do is capture animals again, and you ask, how many of the animals that I captured are marked? The reason why you would ask that is because if they're all marked, what it implies is you probably caught them all the first time, and you probably sampled the whole population the first time. Because what are the odds that you would go out and catch a bunch of animals, and then go back another time and catch them, and they all were marked, if in fact you didn't catch them all the animals that were in that area the first time? More likely, if there were only a small fraction of animals that you marked the first time, that those fraction, when you released them, would mix back in with the other animals, and that at a later time you'd come back and only some of the animals that you caught would be marked. Some of the animals wouldn't. In fact, in a large population, if you only marked a few, most of the animals wouldn't be marked the second time. And the idea is, by using this logic, the proportion of animals that you capture the second time that show a mark, or are marked, reflect the total size of that population that you marked the first time. So if you only marked 10% of the animals the first time, that is, you've only captured 10% and marked them, and then you put them back and then you come back later and catch animals again, you would only expect that 10% of the animals you catch the second time actually have a mark, right? And this lends itself to a formula. So this is how you would mathematically figure out the estimate of a population size using mark and recapture. You would say, okay, well, let's say I went out and I managed to catch, let's pick a number, 15 animals, right? So I managed to catch 15 animals the first time, and I marked them, right? I don't know the population size. We'll make that X. That's what I want to know. Then I were to come back a week later, right? A week later is enough time to assume that all the animals that I collected have gone about their daily lives, and they've kind of mixed back into their world, that their little animal habitat. And now when I come back, I'm assuming that I'm looking at this habitat with this population, you know, with a fresh set of eyes, and I'm catching more animals. And so if every individual in the population has a chance of being collected the second time, same chance of being collected the second time, then what I'm going to be collecting is a set of animals that gives me an idea of what proportion of the population I marked the first time. In other words, if I come back the second time, and now let's say, I don't know, I caught 15 animals again, right? Let's just say I'm just about good for catching 15 in a day. But now only 3 of these animals were marked. If I can assume that all the animals in the population were equally likely to be caught the second time, then what I can do is just say, okay, this proportion reflects the proportion of individuals that I marked the first time. And so this 3 divided by 15 is 1/5. It reduces to 1/5, or 20%. In which case, it argues that I marked 20% of the animals the first time. And so if I rearrange this and do the math, I'd essentially be looking at something like 5 times 15 is the total number of individuals in the population, and that would be, real quickly, 75. X equals 75, right? So this is basic algebra to solve this. And what this tells me is that there were 75 animals the first time. I managed to catch and mark 15. When I released them and they mixed back in, next time I came back, I was only going to catch 3 out of 15 that were marked because I'd only marked 20% of the population. Okay, great. That sounds really nice. It only requires you to come out 2 times and catch as many animals as you can. But how accurate is that? Well, again, we could think, what do we have to assume for this to be a good measure of an animal's population size? Well, in this case, we have to assume that those animals that I marked the first time, when I released them, they mix randomly into the population. In other words, when I come back the second time, I can't be more likely to catch marked animals or unmarked animals than the other kind. Let's say, for example, that catching an animal and marking it totally freaks it out. All right? Now let's say I catch an animal, I mark it, I release these animals, and what they do is they just hide underground for the next 2 weeks. They're just completely freaked out. They don't come out that often. And even if they come out a little bit, maybe they only come out at certain times a day. Now when I come back, I'm not going to see any marked animals. And that's a bias. We assume that bias doesn't exist. Because if that bias exists, what happens is I might catch 15 animals and none of them will be marked. And I go, oh my gosh, wow. Or maybe only one of them are marked. And I said, wow, this is a really big population. I hardly marked any of them. But in reality, I marked a bunch and they're all just hiding. So we have to assume that that kind of bias doesn't exist. And that's an important assumption to know because if it's not true, we're going to have a biased estimate of the population. All right, so let's see if you're following along now. And I've been talking for a while. It's good for me to ask you a question. Let's say you wanted to estimate now a population of whales. So we go back to the populations we started talking about at the beginning. And this is a photo of some killer whales. And you would like to know how many killer whales are in this population. Well, answer this question. True or false, sampling quadrats would be the better method for estimating the number of whales in a population?